Welcome back to the workshop. We want to continue taking a look at section 3.5, multivariate distributions, in particular, two continuous random variables. So we want to now look at the cumulative probability densities or cumulative probability distribution functions. So it looks essentially, again, the same as what we had seen previously, just now instead of one random variable, there's of course two, so it requires the multiple integration. So let's take a look at that. If x and y are continuous random variables, then the function given by, of course, capital F of x comma y is equal to the integral from -infinity all the way up to y, and the integral from -infinity all the way up to x of f of st, integrate with respect to s, the variable that we are replacing x with in the function f, dt, t being the variable we are replacing y with in f. Okay, so we're just looking at the probability that the x and y values are below these specified x and y values. That's it. So it's the same idea that we had taken a look at before. If you wanted a nice picture, if you choose some particular x and some particular y, we are just looking at the probability that our random variable takes on any value inside this region. Okay, anywhere inside that region. Excellent. Now, of course, for most of these, we found that we're only having a non-zero density function on a very small set. Okay, for the most part in the 1 by 1 square. So we'll continue to work with that, and our integrations will become relatively simple then, because for the most part, we're not integrating from or to, from -infinity or to +infinity. So let's take a look at this particular function. And what we want to do is we want to find the joint probability distribution function for this joint probability density function. And we already took a look at this function, so I don't think that there's a huge need for us to really reinvestigate the integration. We just want to understand what integrals we need to perform. So I'm going to first take a look at the coordinate system here, and I want to observe where 1 is and where 1 is. So there's 5 cases that we'll end up with. If either x is less than 0 or y is less than 0, then of course we're ending up where it's 0. So if we end up anywhere out here, then below and to the left is going to be 0, because everything below and left of any point in here, the function is defined as 0, the density function. So the integral from -infinity to these possible values is just going to be 0, because we're integrating the 0 function. So I'm going to call this region I. So that's our first possible location. So let's see here. But essentially, it works out to then split up based off of these two things here. So, of course, the axes, the positive axes we were interested in as well. So the next region that we might consider would be this region here. Now, when I look at points that are below, I do get some non-zero values. So I get values below. So I could call this region 2. We'll handle this a little bit differently. And then the next region that we could end up in that's similar to region 2 is this region, which of course it goes on forever upwards here, and this one goes on forever to the right. And this region we could call region 3. And Let's see here, what else? Well, we could end up with a situation where we're actually inside the region where it's non-zero. Call this region 4. And then the 5th region is where both x and y are greater than 1. So where both x and y are greater than 1, we will call that region 5. So there are 5 possibilities. So capital F, our distribution, our cumulative probability distribution. In fact, cumulative joint probability distribution function, mouthful there. It's going to be piecewise, and it's going to have 5 conditions, 5 different conditions, 5 different locations that it's defined differently for. So there are 5 cases. And case 1, associating to this region, is that for x less than 0 or y less than 0, we have that the function, the cumulative function, is equal to 0, because there's no area between the plane and the surface, because the surface is at height 0. The next condition, or the next area, would be up here. So where we have for y values greater than 1 and x values between 0 and 1. Actually allowing for equality there would be fine. For y values between 0, sorry, y values explicitly greater than 1 and or strictly greater than 1, I should say, and x values between 0 and 1, then what we would have to do is we would have to consider, right, if I choose an x value, I'm just looking at this region here, for example. So I would integrate from 0 to x, and then from 0 to 1, right? 0 to x, whatever our x value is for the x integration, and then from 0 to 1 for the y. So f of x comma y, I'm integrating from 0 to 1 because my y value is above 1, and integrating from 0 to x of, we can call it, of course, s plus 3 halves t squared ds dt. Now go ahead and use Mathematica to evaluate that integral to actually find out what the function is supposed to be. Okay. Region 3, I end up over here if I have some specific y value that's between 0 and 1. So this is for y values between 0 and 1, and x values that are greater than 1. Then our function, our cumulative probability distribution function, cumulative joint probability distribution function, right? If I take that particular y value, I'm going to end up wanting to look at this area here, or that region. So I would integrate from 0 to 1 for x, and then integrate from 0 to y for the y. So, and it's still s plus 3 halves t squared ds dt. For the 4th region, that's the very convenient region. This is where we actually have both x and y between 0 and 1. For x values between 0 and 1, and y values between 0 and 1. Our cumulative joint probability distribution function is the integral from 0 to y, integral from 0 to x, s plus 3 halves t squared ds dt. Again, you want to, whatever this is actually equal to, right? We have to integrate that and actually find it. It has a form. We can perform this integration. You should do this when you're working on your homework. Okay, don't leave it as the unintegrated. Actually perform that integration. So our fifth region, once we're up here, right? Once I choose any point up here, the non-zero, the entire non-zero region is included in that area. So that entire non-zero region should be equal to 1 in order for it to be considered a joint probability density to begin with. So we know that that area should be exactly 1. So for x greater than 1 and y greater than 1, we have that the cumulative joint probability distribution function is equal to 1. So these are the different cases. If I actually wanted to say what the function is, fx comma y, this is equal to, it's piecewise, and it should be whatever that integration was for our first condition, for our second condition, where these are just abbreviating for these, right? In the first case, x less than 0 or y less than 0. In the second case, for y greater than 1, x between 0 and 1. For the third case, we're looking at y between 0 and 1 and x greater than 1. For the fourth case, we're looking at both of them between 0 and 1, and for the fifth case, both of them greater than 1. All right, so you'd actually have to evaluate those. Just to save a little bit of time, I'm not going to worry about it because I've told you what the integrals are. Now I'll go ahead and go to Mathematica, or I think Wolfram Alpha might actually perform the integrations, or I think Desmos might be able to calculate those, or GeoGebra, I believe, can calculate those. Those are all technology possibilities that you can use. All right. If you have any questions about that, feel free to double check with me. As a quick comment, you may have noticed that I did skip over the previous page. It's not completely necessary for us to have, but it's just another comment about using Mathematica to plot regions. So this one I changed a little bit from the very basic things, but I would encourage you to copy and paste this into Mathematica and observe that you can get exactly this thing, which you can enlarge. How do you enlarge it? You would click on the image and then pull the corner of the box. So that's how you would enlarge it. And then you can click on the image to rotate it as well. And that's pretty similar to what you would experience in I gotta remember what it's called here because I just said it, GeoGebra. And GeoGebra could do this too, but not nearly as well, okay? It's a little bit more difficult, I believe. I attempted it and I found this to be easier, so just you could do that. Anyway, so that's what I got for now. Of course, we'll do one more video regarding the cumulative probability distributions, the cumulative joint probability distributions. All right, so anyway, I'll see you guys back in the workshop pretty quick.